So these are the second two step 3 questions from the algebra booklet. There's a really nice question here about whatever this is about, just doing some nice algebraic fractions and multiplying with brackets and things like that. It's pretty nice. This is a horrendous question that I don't want to do. But in any case, we have done it. The first one then is this nice question here, just asking you to simplify this expansion of brackets. It's not hard. This is, of course, a difference of 2 squares, so it's 1 minus x squared. Then, of course, you get a new difference of 2 squares, so it's 1 minus x to the 4. Then you get another one, and so on and so on and so on, until finally you're going to have 1 minus x to the 2 to the n when you multiply all these brackets together. And then, of course, these brackets multiply together. And I think I probably did a bit too much work here to work out what this is, but of course, it's just the next one it ends up being. It ends up being 2 to the n plus 1. All this is just proving that, I guess. But of course, it's going to be the next power of 2, because they all increase by powers of 2 to 4 to 8 to 16 and so on. It's just going to be the next power of 2. So we end up with this here. So that's nice and done. Now it says deduce this thing here. So well, we have this statement here, right? So let's just divide by 1 plus x both sides. Sorry, 1 minus x both sides to get rid of this bracket and have this side be the right thing. So how do we get 1 over 1 minus x here? Well, we can split this fraction in half here, right? And say it's 1 over 1 minus x minus this over 1 minus x. And then we can move this to the other side, and we're basically just done straight away. So that's not too bad. So that's that part done as well. Then it says deduce further that log of this thing is log of this thing. So of course we need to take log of both sides. The problem is that we can't just take, it's tempting to just take log of this side and log of this side, but we can't do that because log of this side over here, all of this is perfect because it's all multiplying, but then you have this random adding thing there. So we can't do anything with the log once we've got it there. So we need to get rid of this random adding thing. Of course, you can't just put it on the other side because then you just start working backwards and get to where you were at the start. So what we need to deduce here, and this infinity sign gives you a big hint here, is that we're supposed to send n to infinity to end up with an infinite number of brackets here, which is where this sum to infinity comes from, but also sending n to infinity, because of this really important note at the top of the question here, which is the mod of x is less than 1, sending n to infinity sends this number here to 0, because you're doing a number less than 1, or a number with size less than 1, to a really, really big number. So that term is just going to go away. This term, of course, becomes infinite, or infinitely long, these brackets. They just go on forever because you're sending n to infinity, which is great, that's fine, because the sum is going to infinity anyway. So now we can take log of both sides, and that's going to be log of one thing plus log of the next plus log of the next. This is log of 1 minus log of this, because of course they're dividing in there. Log of 1 is 0, so it just goes away. And then we end up with this sum to infinity because this sum is going on forever. And it's all good to go, and it's all perfect. We can put the minus on the other side, and we're done. And then finally, hence this thing here. Now, not too easy to see what to do right away here, but I think this term is the one that gives it away. I think they went just far enough to give away what to do here. Like, what is 4x cubed doing? How would you get 4x cubed from any of this? Well, it's the derivative of x to the 4, right? So I think if we just derive both sides, if we take this statement up here, which I'm not going to bother writing with the sum, I'm just going to say it goes on forever. If we take that and just derive both sides, when you differentiate a log, it becomes this thing with the differential on top, which is just minus 1. And then when you differentiate all of these, the same thing happens, right? And that's where all these derivatives come from, times everything by minus 1. And we end up with the answer. So that's part 1 of this question done. And then part 2, really nice. This is my favorite type of step question, really, is when you do all this work in part 1. You know, it talks you through it, does it step by step, and then part 2 just bangs out another one and is like, just do the whole thing in one go, mate. And the way to do these is to look carefully at all the steps that you just used and kind of recreate them in this new example, right? So they're not spoon feeding you this time, but you can still use the hints that you got in the first question. So, for example, where should we start here? Well, we should start all the way up here and come up with some kind of brackets to expand that might work well. And notice how all these brackets here are just the denominators of our final result. So therefore, let's just multiply all the denominators of our final result here and just see what happens. Right? Now, these two things aren't that easy to expand, but once you eventually do it, you work out that lots of things cancel and you end up with this, which is nice. And then when you try and expand these two, you notice a lot of things cancel and you end up with this. And that just keeps going and going, right? I was unsure exactly how much proof was necessary here, but essentially I just went with it and just said that we get to the answer of this here. It's clear that when you multiply them all together, you end up with a thing that looks a bit like this, where you've got a 1, a power of x that is a little bit beyond, or is 2 beyond the one that you had before. So, for example, when we're multiplying these two terms, the x squareds become an x to the 4. So when you multiply these two, you go to the next power of 2 to get the middle term, and then again the next power of 2 to get the last term, like the 4's become an 8. The next power of 2 after 2 to the n plus 1 is, of course, 2 to the n plus 2. So I just said we ended up here. And now, of course, we recreate this step here, which is say, okay, well, all those things expand to make that. Let's divide by this first one here, because that's the one that's shown over here, just like here. So let's divide by that. That makes sense to me. Let's do that. Let's split this up, just following my notes from earlier, split it up, because that's what I did the previous time. And then, of course, what did we do last time? Well, we sent n to 0. Sorry, we didn't quite yet. We moved that thing over to the other side, and then we sent n to 0. Sorry, to infinity, I should say. We sent n to infinity because I wanted to get rid of this term. X is still less than 1 for the whole question. Right, so this will go to 0 if n goes to infinity, and this will just become an infinite number of brackets multiplied together, which is fine because that was fine last time, so it should still be fine. I've just quoted a random one in here, and then it just keeps going, right? Like, I didn't really write that for any particular reason. It just denotes that you hit them all, and then you just keep going. So, okay, and now we can take log of both sides, and then we can, of course, differentiate once we split this right-hand log out. This left-hand log differentiates, this goes away, of course, and we end up with this statement, once we times everything by -1, that they wanted us to get. Thought that was a really nice question. I really enjoyed doing that. Wasn't too tricky, I didn't think. Did take a bit of time to think through some of the finer details, but yeah, just thought it was a really good question. This question I did not like in any way. I hated it. Gross. It was disgusting. I would not have got that. I mean, I wouldn't have attempted this question in the step paper, and I wouldn't have got it if I did. So let's do it anyway. So let's start with the first part. Alpha is a root of this, so if you put alpha in, it gets to 0, that's fine. And if you put alpha in that, it also gets to 0. We can just take these away to get rid of the alpha squares, and then, of course, we can just rearrange it, and we'll end up with what they wanted us to get. So that bit's not too hard. Hence or otherwise, show the equations have at least one common root, in this case, probably alpha, if and only if this thing here. Now, if and only if means we need to prove this if, and we also need to prove the only if. So let's do the if first. So if this thing, so we can start there, if this thing, then this somehow leads to us deducing that these two things have a common root. So that's our first step, and then we'll do it the other way around. So okay, I'm just going to label that star because I think I'm going to use it later. If we divide everything here by a minus c all squared, and believe me, that's the least tricky thing about this to spot. If you divide it by that, you essentially end up with a quadratic in this kind of b minus d over a minus c kind of business. And then you look at this and you think, well, that's not quite right? Because it needs to be something squared plus a lots of something plus b equals 0 to get to this equation here. So how do we fix that? Well, we can just make this whole bracket here a negative, because if we do that, this squares out anyway and doesn't make a difference. And this negative, essentially I'm donating this negative in here to give me a positive there, and it makes now this statement here. So now I'm saying that if star is true, then x equals this thing here is a solution to that equation there, just by this logic here. So that's half of the first half done. I now need to show that this thing here is also a solution to this equation, because that way it's, of course, got a common root. So we've got that bit so far. So now let's shove this same result into there and hope this equals 0 somehow. Not easy to show that this equals 0. However, because, of course, like it doesn't start cancelling straight away. What you need to do is you need to build this result into it. What I mean by that is this bit's good, right? Like this bit is already part of this thing here, which you know is 0. But let's introduce an a lot of it as well, because then, and also a b, only to take away that whole a lot of this bracket and also take away b, because this whole red thing here we know is definitively 0 based on the previous working we had. So that whole thing is 0, which means that then we have this, we can factorize these two things together because it's just c minus a lots of that same bracket. And then, of course, these two things cancel and also get rid of the negative. And then you just have b minus d plus d minus b, which is 0. And so the whole thing is 0. And so this thing here is also a solution to that. And so therefore, if this is true, then we have this thing here as a solution to that and that, which means they have a common root. So the if is done. Now we need to do the only if. So now we need to say, if they have a common root, then show this thing is true. So then we show that, okay, cool. So the common root we've already said is this thing here. So let's just throw that in to the x squared plus x plus b, times everything by a minus c all squared, and we immediately get that. So we're pretty much done. So that was not too tricky, I don't think. So that's that done as well. Then it says, does this result still hold if A doesn't equal C is not imposed? Of course, that was imposed because otherwise this thing is divided by 0. But what if it's not imposed? Well, if A equals C, then this whole statement here just becomes this first term, which means, of course, that B equals D, because otherwise they couldn't square to make 0. But if A equals C and B equals D, look at these two equations carefully. If A equals C and B equals D, those two equations are just the same equation, which means that they'll, of course, have a common root because they're the same equation. So that's that done as well. Then we get to part 2, which was the trickiest part about this question, I thought. Show the equations. And what I thought was tricky about this was because I wasted a lot of time trying to, just like we saw in the previous question, replicate the same method for part 1 for part 2. Like I was like, okay, well, first we need to describe alpha, and then we needed to go through the same steps they did. Then we need to show, and then we'll be fine. And that's not really what you do here. What you do instead is you do the other thing that you do in step a lot, which is you try and work out how to make these things here relate as closely as possible to the initial things you were given. You try and transform them into the initial thing. Of course, if you just throw in alpha, I think I just did it anyway. If you throw in alpha to both of these, there's not really an easy way to get rid of alpha. Um, like you can't just take them away because the squares don't go away because there's a cube here, like it did nicely there. And also, even if you'd like times this one by alpha, which I tried, which actually is something you do something similar later, but even if you just times this by alpha, you end up with an alpha squared, you end up with a quadratic, which you can solve for alpha, but it ends up being a mess to work with. So that isn't really the way to go. What you want to do is you want to relate this to this as closely as possible. Notice how similar this is to this, in the sense that if R was just D, and if C was just Q minus B, because here you're doing A minus C. So, but here's an A plus. So if you made C the other way around, if you made C Q minus B, then when you do A take away C, that would be A take away this, which is take away minus B as a plus B and take away Q as a minus Q. So if you replace those out, you end up with the statement that you had in part 1. So, okay, we kind of made these substitutions here. So we've made those substitutions. We've got rid of those things from here and put these instead. I guess I should have said sub out R for D here. Oh no, I guess I'm consistent here. So sub out from here, sub out D for an R, and sub out C for a Q minus B, and you get to this line here. So I guess I'm just saying it backwards. Anyway, you end up here, but of course, because we've already shown an if and only if statement in the first part, we know that the fact that this is sitting right here implies that these two things have a common root, because we proved that in the first part. And that root was that thing, I think. Not that it really matters. So, okay, now we can replace the C and the D back with their original letters, just putting the substitution backwards. And now we still need to relate these to these two equations, because we're trying to show that if this is true, then these two have a common root. Well, we can actually do that, because we can create this expression from these two. If we times this one over here by x, and now if we times it by x, we introduce a solution at x equals 0, but that doesn't matter because we're looking to make a common root of something else. It still has exactly the same roots that it did before, right? Even if you've introduced that x equals 0 root. Keep this one the same. And now if we add these two things together, what do you know? You end up perfectly here. And of course, if let's say some alpha is a root of this and alpha is a root of that, when you add them together, they're still equal to 0. Alpha is still going to be a same root. So therefore, this thing here and this thing all the way up here share a root, because this thing does with this, which means it does with this. It still has the same root here, and then when you combine them, it's going to share it with here. So these two things have a shared root, and we've shown if this is true, then this and this have a shared root. Okay, so that's the if part done. Now we need to move on to the only if. So we need to show if there's a common root, or at least one common root, then this thing is true. So we'll start by just putting in some alpha into this and putting in some alpha into this. This is similar to how I started and how we started this question up here. We can't really eliminate the alpha very easily, but I've given away what to do earlier. If you times this one by alpha, similar trick to before, and then you try and add them, take them away to get rid of the alpha cubes, you end up here. And now what you could do is you could try and rearrange this for alpha and end up with a quadratic formula for alpha, I guess, is one topic, is one idea. But what you can also do is you can put that same substitution in that we did last time to end up here. But what you know is that because of the first part, and this is a tricky thing to spot, but remember the first part was if and only if, right? So we showed that this thing here was true not only that implied there was a shared root here and here, but it also meant that if there was a shared root, this was definitely true. Now, what this is saying here is that this thing and this thing have that shared root of alpha, right? And so therefore, this thing is definitely true from part one because of the only if bit, because it works both ways. But of course, now we can put the substitution back again, and we end up exactly here. So putting those substitutions back and forth is kind of a tricky thing to spot there, I think, and that's certainly the thing that would have gone over my head, I think, if I was doing this in a real exam, but that's all that done for now. And now we finally end up with hence or otherwise, and this is the easy part of the question, actually. Find the common root here. You could have done this even if you hadn't managed all this proof, I don't think, because you can just divide this by 2 to end up making it look like this. You can divide this one here by 2 to make it look like that. You notice this works beautifully because ax is 5 over 2, so a has to be 5 over 2. But here you've got an a plus 1, which happens conveniently to be 7 over 2. So it's all consistent. These are the numbers you're working with. B is just B because it is just B, I guess. And then you just throw that into this formula, and you can solve for B. And it's really not that tricky. Everything kind of expands out. You can times everything by 4 at some point. You end up here. And then, super easy from here because all you have to do is spot that B is 1 is a solution. 4 minus 6 is minus 2 plus 1 is 0. Factorize it out. You can do some polynomial division if you want. I just spotted the coefficients. I've got a minus 4b squared, so I need another minus 2, lots of them, to make minus 6b squared. And then we can use quadratic formula on this. And we end up with 3 solutions at b equals 1 and at these 2 things here, which you can eventually simplify a bit further to get all the way down to there. And that's that question done. Thank you so much for watching.